From pairs we build a world of thought, of functions rule a path we sought. Equivalents for grouping, orders for ranking, each elements find its spot. Relations link the mind to heart, a logical and elegant art.
Previously, we introduced the concept of a function as a map from a set A to a set B. Looking at how a single point is sent to another point may not fully reveal information about the bigger picture. Instead, it is more useful to see how functions transform a subset from the domain to the codomain, and vice versa. For example, consider two functions from R2 to R2. One sends xy to x minus 1, y plus 1. The other sends xy to negative yx. If we only apply them on the point 1, 0, then both functions map it to 0, 1 indifferently, but when applied to a whole subset, the geometric nature of each function becomes clear, and we can see the former is a translation and the latter is a rotation around the origin. This motivates two fundamental notions, the image and the preimage. Let f be a function from A to B. For a subset C of A, the image of C under f is the set of all elements of the form fx, where x is in C. For a subset D of B, the preimage of D under f is the set of all elements x in A, such that fx belongs to D. Intuitively, the image describes the consequence of applying f to a subset of the domain, while the preimage describes the reason behind a subset of the codomain. Let us first look at some very trivial cases. Let f be a function from A to B. It is vacuously true that the preimage and image of the empty set is empty. Now consider the whole set B. The preimage of B is the entire set A, because every element of A is mapped into B. On the other hand, the image of A is not always the whole set B. Instead, it is in general just a subset of B, called the range of f. In some cases, the range of f is equal to B itself. In other cases, it is a proper subset of B, as some elements of B may not come from any element of A under f. For example, let f be a function from R to R, which maps x to x squared. In this case, the image of A is the interval 0 to infinity, which is a proper subset of the codomain R. Before we proceed, pay attention to the following subtle differences between the notations. This is the function value at x, which is an element in B, while this is the image of the singleton x, which is a subset of B. This is the inverse function value at y, which is an element in A, while this is the preimage of the singleton y, which is a subset of A. Our next example is the indicator function. Let A be a set and S a subset of A. Consider the indicator function from A to the real numbers, which sends elements in S to 1 and elements in the complement of S to 0. Given a subset C of A, if C is a subset of S, then the image is the singleton 1. If C is a subset of the complement of S in A, then the image is the singleton 0. If C intersects both S and its complement, then the image is the set 0, 1. Now let D be a subset of R. If D contains both 1 and 0, then its preimage is A. If D contains 1 but not 0, then its preimage is S. If D contains 0 but not 1, then its preimage is the complement of S in A. Finally, if D contains neither 0 nor 1, then its preimage is the empty set. Let's look at another example. Define f as a function from R2 to R, where fxy is the distance from the point xy to the origin. Let A be the region on and above the hyperbola xy equals 1 in the first quadrant. We want to show that the image of A under f is the interval square root 2 to infinity. To build some intuition, consider circles centered at the origin with radius r. For small r, the circle does not meet the region A, so those radii cannot be achieved. As r increases, the very first contact happens at the point 1, 1, which has distance exactly square root 2 from the origin. From then on, every larger circle intersects the region A, meaning all radii r greater than or equal to square root 2 are achieved by their points in common. So geometrically, the image is indeed the desired interval. Don't forget, though, that the desired equality is a set equality, which must be justified rigorously by proving both inclusions. For one direction, given any point xy in A, the AMGM inequality implies that x squared plus y squared is greater than or equal to 2xy, which is at least 2. This shows every point in A has distance at least square root 2 from the origin. For the other direction, take an arbitrary r greater than or equal to square root 2, and consider the point r over square root 2, r over square root 2. Their product is at least 1. Hence this point lies in A. Moreover, direct computation shows that its distance to the origin is exactly r. Hence, every such r can be achieved as the function value of some point in A under F. This proves the other inclusion, and hence the desired set equality. We have now seen the definitions of the image and the preimage, along with some examples. Next, we will study some of their elementary properties.
新了 tensei